Okay, cool. So in my part of the lecture, I'll cover three topics. I'll be first going over positional encoding, which basically discusses how we can incorporate positional information into our word embeddings. And then I'll be going over attention inference acceleration, which is which are methods that combine attention matrices to accelerate attention at inference. And third, IO aware based attention acceleration methods. So let's get started with positional encoding. So before we talk about the mechanism, the first mechanism, rope, let me talk about why we need positional encoding. So suppose you have a you're feeding a sentence into transformers, and you have a lot of words. In particular, you have W1 to, let's say, WN. And the first thing that you do is you feed them through an embedding layer. It's called that, like E or something, and then you get vectors x1 to xn. These are the outputs of the embedding layer, and W1 to WN are just raw words. And you feed x1 to xn. You combine them into this big matrix X. And you say, okay, for every xi, I want to get matrices Q, K, and V. So the way that we do that we have three matrices PQ, PK, and PV, and then we do X, PQ equal to Q, and then the same for K and V. And you can see what happens here is that x1 will be, this is effectively doing multiplying, this here is effectively saying x1 PQ, xn PQ. Because we first multiply x1 by the first column PQ, and then the second entry will be also x1 multiplied by the second entry of PQ, which is exactly what we're going to get here. But the point is, throughout this entire process, the positional information is not encoded. Here in the embedding, the embedding function, it doesn't take the index wi. It doesn't take this I into any consideration. And here, when we map it to Q, the PQ, when we multiply the matrix PQ, it's just the matrix multiplication. So it also doesn't take the information, the positional information of the particular word into account. And when we later on do QKT and take the softmax of it and multiply V, you see there's still nowhere do we consider the positional information. So in a way, the positional information is lost if we just do raw transformers and don't look at the positional encoding at all. So that's why we need positional information. And originally in the Attention is All You Need paper, there were two ways to combat this problem. So one way is to use sine cosine functions, and then we basically, what we do is we add to each of these xi's some sine and cosine values. I'll be going with this later. Just to give you a brief on the other approach that was covered in Attention is All You Need, there were learned positional embeddings that we could apply to each of these words. So to talk about the sine cosine sine cosine functions first. Basically what we do is before we apply, so here is basically what we just talked about, except they wrote it in w multiplied xi. I wrote w x times p, q kv. So what we do here is for each of the xi's, we multiply, we add a positional vector to it. And basically this positional vector I is going to be heavily dependent on what this I is. And see, this is the pi here. And at each position of xi, so suppose that xi is this long vector, at even indices, we add sine of I over 1/10,000 2t over d. And at odd positions, we add sine of I over 10,000 2t, cosine over d. And I is the positional vector at I, so as you can see, this pi will be heavily dependent on what I is, and it's going to be unique to the specific I. And t here is the index within within pi, because pi is it's not a single value, it's an entire vector. So here t would be equal to 1, here t equal to be 2, and it's going to increase as we go along. So it's basically pi is going to be a unique combination of these sine and cosine values, and altogether they're supposed to transmit a unique signal. This vector is supposed to transmit a unique signal depending on what this I is. So by adding this positional vector to xi, well, our goal is to retain some information. Before we feed it into the attention part, we want to add some signal so then the attention part can know that, hey, this is maybe the ith position, because we've detected some signal here with the addition of pi. And there's been an ablation study that has shown that we can actually learn based on the positional encoding, the absolute position of the basically we know that given xi plus pi, we can learn I with a linear regression. So basically this is why we kind of need a positional encoding in the first place. Okay, so how does rope encode the positional encoding? So I'm just gonna bring you back to here. So we don't necessarily have to encode the positional information at the sinusoidal stage. Consider the following setup. So we have wi, goes through an encoding, becomes x, and then it goes through these projection matrices, and it becomes q, k, and v. And what we can do is that we're gonna say we believe that for q and k, here like each entry, the ijth entry of this matrix is q, I, t, kj, we're gonna say for I and j that are far apart, then this signal doesn't matter so much. But for I and j that are close, this signal is gonna matter a lot, and then we wanna kind of convey this relative position information into the transformers. So yeah, so that's the idea. So the way that rope does it is that basically the idea comes from in the complex plane. In the complex plane, if you want to rotate a vector x by theta, you multiply it by e to the I theta. So here we say, in rope we say, if we want to rotate it, for xm, we rotate xm by m theta, and we rotate xn by n theta. So as you can see, if xm and xn, which are assumed to be in the roughly the same area, that they're being mapped to by the word embedding here. Suppose that maps to like a particular area that's rather a small part of the whole in higher dimension. If m and n are close, then they're rotated to roughly the same area. But if m and n are far apart, then they're also going to be far apart. And what that really means is that here we're really not rotating xm anymore. We're rotating like qm and qn and then km and then kn. What this means is that when we take the dot product here, the dot product is basically going to be small, because we call that the dot product is going to be, basically it's going to be, okay, maybe this is not the right symbol, but basically it has a term of, it's equal to qi kj multiplied by the cos of the angle between them. So if this is rotated by m theta, and this is rotated by n theta, then the cos, the theta here is going to be something like m theta minus n theta, plus some like smaller value. So if m minus n is large, that means the theta is going to be large. So then the cosine value is going to be small. So then the signal won't be as big. But if m and n are close, then the value, this dot product is going to be large. So that's a way of telling the transformers to keep the dot product large if I and j are close, but keep them small when they're far further apart. And the way we do that in the complex plane is multiplying by e to the I of m theta. But if we consider this, the complex plane, to be a bijection to the R2 plane, okay, first of all, e to the I m theta is equal to cos of m theta plus I sine of m theta. And then if we take this to be one coordinate and we take this to be the other coordinate, this is the imaginary coordinate and this is the real coordinate, and we multiply it to some arbitrary number, we'll basically get that multiplying by this number to this is multiplying by a matrix to this, and that matrix is exactly this here. So basically we successfully mapped this from C to R2, and the way that we rotate a vector in R2 is basically just multiplying by this matrix here. And I won't go into more details about this. And if we want to do this in higher dimensional, say D-dimensional space, what these guys propose is very simple. So suppose that we have this vector here. This is basically either QM or KM, and it looks something like this. We say that we take every pair of coordinates and we rotate the first pair by m theta 1. We rotate the second pair by m theta 2, and so on and so forth. And by the way, we keep the theta i's to be this, which are relatively smaller numbers. They're smaller so to ensure that we don't rotate a full cycle. So basically, if m and n are actually far enough, m minus n times theta I, it's equal to like 2 pi or something. So then it actually means that m and n are like kind of close. So we don't want that to happen. So we keep it small. And yeah, so this is what I talked about. Keeping basically we want to apply the positional encoding during the matrix multiplication between Q and K. And this is Q, this is K. This is basically QM, this is KN, and we rotated this by n theta and this m theta, and that's basically equivalent to multiplying by this matrix here. If we take the transpose of everything, basically what we can do is multiply these two first, which look like this. And when you multiply this by the transpose of the other one, which is going to be the negative theta, you're going to get m minus m theta. And we can actually do the m minus m theta very fast. So we don't actually have to multiply this huge matrix right here by another huge one. We can instead do this quick operation here. And we can continue doing this for linear tension, because common choices of the map here basically is just like a normalization scheme. So like they're still around. So this is like Q and K, and then this is like phi of Q and phi of K. Like they're still around the same area after a normalization scheme. So rotating them, I guess the idea is that rotating them would still work. Okay, so another thing to note is that sinusoidal encoding is applied at the very beginning. So applied right here. When the word is mapped to embedding, we add, here we add like a positional encoding PI. Yeah, like here. And it's only applied once throughout the entire transformers architecture. However, for rope, it is applied at every Q and K. Every time you multiplied, you do this, you apply rope. And yeah, this is like a bound on basically saying that if you have two things that are far apart, this is the relative distance. So this is basically m minus m. This is the upper bound, and the upper bound of how large their dot products between the rotated QM and this multiplied by QM, and then the multiplied by the rotated KN. How far? Okay, there's no T here. So basically, how far these could be, and it's saying basically when n minus m is large and they're far apart, this bound goes down, which is kind of what we want. So here is how rope performs. So as you can see here on this task over here, it does a bit better. And on these tasks, on these downstream tasks, it performs better for some of them. And for the mask LM scores, basically, row former, which the blue line is lower. Same for LM here. This is masked. This is just normal LM, and it's used by GPT-3. Okay, so that was a very fancy mechanism, and let's look at the next mechanism, which is called ALiBi, and it's much simpler compared to the previous one. And the motivation for ALiBi is that models can take arbitrary long input lengths. Transformers models can take arbitrary long input lengths compared to what it has seen during training. So again, if you recall, what Transformer does is basically it multiplies this X, which is your embeddings that came from words. And suppose there's n words, and suppose the dimension of each of them is d, and when you project it to matrix Q, it multiplies X with the matrix Q, which is of dimension here, d times dq. So therefore, however large n is, we can always multiply these two matrices together, and transformers will also always work. The thing is, when we train on shorter length x's, it's usually unable to generalize well to longer length x's at inference time. So ALiBi overcomes this, and it's able to extrapolate to longer sequence lengths. And again, we've considered sinusoidal, which is intention all you need. Rope, we just covered this. And there's also another learned embedding called T5 bias. And the idea is that, sinusoidal is the worst, and then rope, and it's T5 bias. But ALiBi is still better. And another idea is that we might want to compute we don't want to compute the exact context length that was fed in. Like, another argument is that this might not be a fair comparison, and what is actually fair is if we consider the amount of compute it takes, because sinusoidal is much lighter. So for example, for sinusoidal, maybe training like the length of 1024 is same as training at the same transformers with the T5 bias, with like context length 512, because T5 bias takes up more compute, so training this and training this actually takes around the same compute. So what ALiBi does is it basically adds, so for query I, it adds query I dotted k is like you have one q here, and you have like a huge k matrix. You do this multiplied by this, and you get like this value here, and then you get this multiplied by this, and you get this value here. And basically at this position here, this is the ith out of like many. Here we add minus I minus 1. Here we add minus I minus 2 all the way to 0. And then 0 is after that. Yeah, the reason that we add this is for the same reason as before. For I and j, j is like the k index. For I and j that are far apart, we want the qi we want qi dot k, we want qi kjt. We want this value to be relatively smaller signal to our transformers model. Because in a way it doesn't matter as much. And the reason that we have zeros all after that is because we want to add a mask so that the transformer doesn't cheat during training. So basically, we have like what do we have? We have like, my name is Matt, and during training the first Q is gonna be like on my, and if we're trying to do language modeling, K is also gonna be on my, and then so that's gonna be like the first one, and then Q is gonna have basically this is basically WQ times X1 equal to Q1, and then we're gonna have sorry, this is not, and then we're gonna have name is equal to like X2, so we're gonna get Q2 here, and the idea is that when we're doing Q1 times KT, we don't want to be able to get K2, which tells us about name, because this is equal to WK times X2, and X2 is based on name. So we basically, if we're trying to complete if we're trying to complete the sentence QI, like if we're trying to complete the sentence my, we don't want K2 it already tell you what the next word name is. So yeah, that's kind of the reason we have zeros all after that, because we add a mask anyways. So yeah, this is the same idea, and M is a head specific constant specified before training, and this is with n heads, this is what we set M to be, and that's just I guess the number that worked well for them, and they observed that trainable M's didn't work well, and slopes between 0 and 1 that had a higher density around 0 worked well. So yeah, so this is, each head is going to have a different M, and therefore it's going to take L times n space, where L is basically, we kind of like mixed up the terminology here. L is the length of the context, and it's L times L because that's the size of QKT, and you kind of have to have a different n for every head. So it's a different M for every head. So you keep a QKT for every head, so that's why it takes that much space. So it's also applied to every layer, just like sinusoidal. We can also talk about perplexity here. So this is just basically explaining what perplexity is. So we want the LM to be able to assign real sentences high probabilities. That's the idea. And perplexity is some function of this probability function. So basically, lower perplexity is better. And just a comparison between ALiBi versus sinusoidal. With ALiBi trained on half the tokens compared to the sinusoidal one, ALiBi performs around the same as the sinusoidal one when tested on the longer sequence that sinusoidal was trained on, even though it's faster and uses less memory. And here's some results. They're all trying on 512 tokens here. As you can see, ALiBi stays pretty good, while the others just diverge. And the same here for 10,024 tokens. And here you can see that ALiBi extrapolates pretty well, trained on 512, where sinusoidal, when trained on 512, it does basically performs here, and you don't really see the next one because it explodes. And that's the same phenomenon here. It just explodes. Sinusoidal performance just is very poor as soon as you increase the input length by a little bit. But ALiBi does fine. And here's the validation perplexity. And it shows that ALiBi trained on half the tokens does just as well on the tokens basically that plain sinusoidals gain here basically on 10,024 tokens, and here is basically 2,048 tokens. Okay, so now I'll be going over multi-query attention. Multi-query attention is basically reusing the same WQ, K, V, K, Q, K, V matrices across different heads. So usually we would have one of these for every single head, so it looks something like this. But now we use this. If we use the same one, then it looks something like this, and that's supposed to give us speed up because we only have one matrix. Attention basics. I won't be going over it again. And yeah, let me just. I won't go through the in-depth analysis here, but let me tell you what each of these variables mean. So basically, X is your input matrix, and it has context length n. And this is the input to your encoder. And this is the M is the input to your decoder basically. And then this has length m. D is the size of every word embedding. H is the number of heads. B is the batch that you're taking this over. And yeah, K and V are the sizes of W, K, and WV. And yeah, I think that should be all. And basically what we want is we want the total memory access of multi-head attention to be, and not to confuse multi-head attention with multi-query attention, which is what we're covering here. Multi-head attention is the original attention mechanism. Suggested in attention is all you need. So here we have memories to operation ratio for training. You know, it's a lot less than 1. It's 1 over K. And K is the value here. And plus 1 over Bn, which should be a lot less than 1. But for inference, it becomes n over d plus 1 over b. And 1 over b, it's easy to deal with. We just increase the batch size to be larger. But n over d is something that we might need to worry about. When our context length is roughly, for example, if our context length is like 1,000 words or something, and our d, the value of d, which is the dimension of each embedding, word embedding, it's also like around 1,000. Then we might need to worry because this is not a lot less than 1 anymore. And so yeah, it's a very simple idea. We just basically use one we can see here we had the pk, we had h of them for each head, and then d times k. But as soon as we use multi-query attention, it's now just dk and dv. And I guess here we don't actually need to worry about PQ here, because we're dealing with an encoder decoder task. So the bottleneck comes from repeatedly reloading k and v. So if you think about it, if I want to like do inference again with like my name is Matthew, and if we wanted to like translate it into like French or something, it would be like je m'appelle. Okay, my French is not good enough for this. Mathieu or something. So so suppose that we're doing this task, and we start with the word my. At inference, what we need to do is at inference we have this entire query. My name is Matthew, and we want to translate it. And the first time we're gonna get je, and then the PQ, or like the Q matrix, is gonna remain the same. Q equal to PQ times X, but K and V are gonna equal to PKV multiplied by M. This M is going to keep on changing. The input to our decoder is going to keep on changing, because after the first word we have je, and then we have m'appelle, and then we have je m'appelle Mathieu. So we're going to have to keep on reloading this K and V, and that's where the bottleneck comes from. So yeah, during training, it still does pretty well. No surprises here. But during inference is where this multi-query attention really shines. So before, where we have n over d, which is what we wanted to reduce, now we have n over dh. We basically, because we reduced the number of k's and v's that we want to reload by a factor of h. It shows through here. So then the memory to operation ratio is again kept low, and that's why multi-query attention works pretty well. Okay, so let's look at some results. So here are basically how they perform. You can see that multi-head still performs the best, because it does have more heads, but multi-query is comparable to it, and the same for here. Multi-head is the best, but multi-query, it's comparable. And to look at the time that we saved, here again, if you look at the encoder time, it's all around the same, because Q remains the same. This is the translation task, so Q remains the same. It's always going to be my name is Matthew, but multi-query attention really didn't speed anything up there. But for the decoder part, we have to constantly reload je m'appelle Mathieu. So by doing that, we waste a lot of time if we reload h times as many more heads in multi-head versus multi-query. So yeah, so that's a lot faster here. Yeah, so there's still some problems with multi-query attention. They're basically just two big problems. The first problem is that if we already have, we did like the OpenAI trained GPT-4, spent like $2 billion on it or something, and then now you say, oh, what you really should do to speed up your inference is use multi-query attention. But when you started training the model, you used multi-head attention. So what are you going to do now? Are you going to train the model from scratch and spend like another like $1 billion on the training, or is there a faster way to adapt your existing model to multi-query attention so it's faster during inference? So the answer is affirmative. There is. It's called uptraining. And another thing is that we want to find an intermediate stage between having, like in this example, having eight, like here there's 8 heads all sharing one KV matrix, and having 8 separate KV matrices. We want to find somewhere in between. So what if we have like 2 of them, for example? So that's called group query attention. That's what we're going to cover next. So we're first going to cover up training, and the idea is very simple. So we basically have our original. For example, we already had our original, k different projection matrices, and we take the mean, and we say, okay, now we have a new projection matrix, and this might not work well at first, but we're gonna say, okay, we're gonna train it with multi-query attention, and then it turns out if we just do 5% of the original training steps, this matrix turns out to be good enough. We can also randomly initialize it. It doesn't work as well, and we can also initialize it from like a particular key projection matrix. Also doesn't work as well. The mean pool works the best. And for the other thing I was talking about, instead of having only one, we can maybe have like 4 and separate these heads into 4 groups. So 2 of them share a single one. So this is sort of an in between. And uptraining can also be applied to group query. Namely, we just pull these 2 heads, mean pool these 2 heads into this one and train. Okay, so the benefits of group query attention. So one is that it might be like a natural trade-off between MQA and MHA, between performance and time. It's gonna have, in terms of speed, it's gonna be somewhere in the middle, but in terms of performance, it's also going to be somewhere in the middle, and it might be the best middle ground. And moreover, if you consider MQA, where 8 of these heads all share a single projection matrix. In standard charting, this matrix might be, these 4 might be grouped into one shard, and these 4 might need to be grouped into another shard, and this projection matrix here would originally have to been copied twice, anyways. So that's kind of saying if it was gonna cost this much memory anyways, why not just do GQA? And now in terms of GQA results, as you can see, in terms of time, it's comparable to MQA, but it beats MQA in performance. In terms of performance, it's comparable to MHA, but it beats it in time. And here's a graph showing the trade-off between GQA as the number of groups increase. So at 1, basically, GQA is basically equivalent to MQA. But as you scale it up, it's gonna take, it's gonna take more time to sample, and that's basically shows the trade-off. And here, it shows the trade-off between, again, time and the performance. So as you can see, MHA here has the highest time, but also has the performance, and MQA has the lowest time, but also decent performance. Let's ignore this one. Out of the 3, has the lowest performance, and for GQA with 8 groups, it has relatively good time and relatively good performance. And here are the results for uptraining. As you can see, when we take the mean, that achieved the best performance with alpha equal to 0.05. And you can see here with alpha equal to 0.05, we can kind of achieve comparable performance with GQA and slightly worse with MQA than with 1%. basically identical performance with GQA and worse with MQA. Okay, and now I'm done my section on group query and multi-query attention, and I'll move to IO-aware based methods, namely flash attention. So basically, previous attention speedups, many of them, for example, they have sparser attention or low rank approximation. They what they don't focus on is being input and output aware. And what I mean by that is using the SRAM, the in-chip SRAM, in a smart way. They don't take that into consideration. And flash attention thinks about this and uses SRAM in a very smart way, so that there are fewer access to HBM, which is basically a larger but slower memory. Yeah. So to give you some basics about this HBM and SRAM, there's like 40 to 80 gigabytes of HBM. It's not that fast, and there's a much smaller SRAM unit, but it is much faster. So the idea is that instead of doing many trips of HBM reads and writes, like suppose that this is the HBM, and this is your SRAM. This is your CPU, or sorry, GPU. This is where you like. This is where you. This is your unit. This is processing unit. Basically, you can think of it as retrieving information. If you keep on, sending stuff from HBM and then sending it back, going forward, sending it back, it's going to take a long time. But if instead what you do is you say, okay, first I'm going to read from HBM, and then I'm going to put some intermediate back, not all the way back to HBM because that's going to take way too long, but I'm going to put some intermediate back into SRAM, and then process again, and then do some of this, and then go all the way back to HBM. That's going to be a lot more cost effective, and that's the idea behind flash attention. And just for some reminder of the matrix dimensions, and storing takes O(n) squared memory because of this, yeah. So let's get into flash attention. And before that, let's just go over standard attention again. And this is the thing I was talking about. Going back and forth between HBM and the processing unit. So here you load from HBM, you write it back, you load, you load it, you write it back, you load it again, you write it back again, you load it again, you write it back again, and finally you return it. That's not the smartest way to do things, and it doesn't really use SRAM to speed this process up. So the idea is that we can use SRAM. Well, how can we use it? So first of all, we can use this method called tiling, which basically says, okay, so this is your SRAM here. You break it up into a few different slots. We dedicate one slot for the Q, one slot for K, one slot for V, and one slot for O. And then here we dedicate two, smaller linear slots for L, and then another for M, and I'll explain what they mean after. So the final goal of what we want to achieve. So suppose that we started with your X's. What we want to do is we want to compute your Q, K, T, and then we want to take the softmax of it. And the reason, okay, so So okay, so what does the softmax function look like? Okay, so suppose that this matrix. Okay. Suppose that this matrix was only a single vector. What we want to do is take the exp, we take it to the exponential, and then we subtract by the maximum. And then we divide it by this L, which is the sum across all of them. This is L. And that's basically our end goal. Now, because the SRAM is so small, each time it's impossible for us to load an entire Q or entire K or entire V. So we can only compute a very small part of it, at once, and we'll have to concatenate them together. The problem is that there is a softmax outside of QKT. So, if our final goal is this is without the softmax QKTV, just for illustration. And basically this is our O without the softmax. If our final goal is to compute something like this, and each time we only have like Q like a small component of Q. So suppose that this is an entire Q. This is Q, and each time we only load a little bit of Q, and we load this is K. We only load this is KT. We only load a little bit of K. So that means out of this entire output, we only have like Q from 1 to like maybe like somewhere here, and then K. Q goes this way. Q goes this way, so Q1 to like somewhere here, and then K from here to over here. So we only have like this part, and then what we have to compute is we compute this, and then we compute this, and then we compute this, and we compute this, and then we compute this, and then add it to this, and then we compute this and add it to this, and then etc. So let me just draw that more clearly. First compute this little part, and then this, and then this, and then compute this, and then add it to this, compute this, and add it to this, compute this, add it to this. Now the problem is that if we have to take the softmax, so we can't just compute this and take its softmax, and then compute this and take its softmax and add it to this. You know, that doesn't work like that. You're gonna get the wrong softmax values. So that's why we need to keep an array of M, which is basically the maximum of this row here, and then another array of L, which is basically the sum here. And we're gonna use this to finally compute the correct softmax at the very end. Okay, so how do we do it? So high level idea. What we do is we start out with this. Yeah, maybe let me just go through the pseudocode, or yeah. So the high level idea is that we do this, and then we do this, and we do this, and we do this, and then when we get to here, basically we normalize this by some factor. And when we get to here, we multiply it by that factor again, and then divide this by the softmax for the entire thing, and then we repeat. So then when we get to the very end, we basically are multiplying. We have the entire thing divided by the L factor for everything. So yeah, so let's take a look at the pseudocode. So we first loop on K and V. That means the inner loop is on Q and O. Yeah, maybe we should have this Q, O, K, V. L and M. This is our SRAM chip. We initially load K, Ki, Kj, Vj, which is basically like a subset of K and V. You can think of the entire matrix of K like this, KT, and then Kj is like some number of columns of K, and then V is some number of Vj. This is KJT. This is like VJT, and this is V, and the same for Q and O. Okay, so we load KJ VJ on from HBM onto SRAM, and if you look at the final outputs of Q, KT, and V, that means we're trying to narrow down for, you know, like for example, if J only includes 2 rows, then we're only looking at this group here. And then we loop over Q, which means we go down this way. So then we first load Q, and then we load Q and O. So we load the first one, and then on chip we compute Qi, KJT, and so we first compute this, and then we compute this, and then we compute this. And the question is, what do we do after every single one of them? Okay, so as an example, we first compute this here, and we compute the max of this row, and then we normalize it with, we take this row, and then we take we take its value, and we take it to the exponent. So we do exponent of all of these values to it. Oh, by the way, this is not the this is not the intermediate value. This is the, what I should really be doing is towards this. This is QKT. So we take a small component of it, like somewhere here first, and then we look at each row. So for the first row, we look at the max, and then we do the exponent to this value minus the row max, and then the next value minus the row max, next value minus row max. And then we look at the next row, and we say this row, this value, e to the this minus the max of this, etc. And then we divide it by this L. And then we say, okay, so let's look at if this maximum value, so suppose that we were like somewhere in the middle here, if this maximum value were the max across all of these previous values. So if we already did this part, and we already did this part, and then we're like looking at this partition, so maybe like the third K, K3 or something, and then we're looking at Q1, and we look at the maximum here, and we say, oh, is this maximum, you know, is it larger than the previous two? So and then we take the maximum here, we take the true maximum here, and then for the previous two we have the previously computed maximum here, and then we basically multiply it by that maximum to get rid of it in the previous two terms that was already saved in the previous O, and then we subtract by the true maximum, because we need to divide everything by basically e to the negative mi prime, and then we do the same thing for our current one. We want to multiply it by whatever it currently is, divided by the global maximum. And then what we want to write to OI is basically we want to have our original OI. So we already computed this, now we're somewhere here. We want to normalize it, we want to multiply by Li, because we divided by that Li before, and we divided by the global softmax, true softmax, and yeah, we do the same thing on our third one here. That's this term, and this is basically these terms that was already written. And we rinse and repeat, and then we compute the entire thing. So yeah, hopefully that was clear enough. So flash attention guarantees. So it requires of an additional memory, which comes from L and M. But of course it requires way fewer HBM accesses, because basically we already do all the intermediate steps. We're basically do on the chip, and then we basically do one final write at the end. Yeah, these are on the chip, right? So yeah, and they prove some theorem that says in terms of memory access complexity, there's nothing better under some mild assumptions. And the next thing is block sparse flash attention. It's basically an addition to this. So in block sparse attention, basically, in this matrix here, basically we say, oh, for these, we only care about, like, for example, like the center ones, and for these, like, we don't really care about them because they're too far apart. And that's very easy to do. You know, just chop this QKT into blocks, and set this to 0, set this to 0, set this to 0. And during the for loop, you know, just skip it. Just do a continue statement in that for loop, and it'll, you know, just it won't assign anything to it. So yeah, then in terms of its results, yeah, you know, it's much faster than before. And yeah, again, the performance should be the exact same because we're not really changing anything inherent to the model or model training. All we're doing is changing the way that we read and write on numbers. And again, here it shows the speed up. Here's the training time. And as you can see, it does a lot faster. It's a lot faster than before. I only covered the forward pass. There's actually additional backward pass. You can check it out in the appendix of the flash attention paper. So flash attention is the black one. Block sparse flash attention, of course, is the fastest, and then it's the green one, and then it's flash attention. Actually, Linformer beats it sometimes, but it's kind of cheating because, you know, flash attention is still O of n squared. You're still storing the entire QKT matrix, whereas Linformer, I think, is only storing something linear, or the computation is linear. Okay, so flash attention actually also achieves, in particular, some pretty amazing results on path X. So what it does is it achieves non-random performance on path X, where it is the first transformer to achieve she achieved this non-random. Sorry. So flash attention is also the first to achieve non-random performance. It is the first transformer to achieve non-random performance on path X with 16K context. And flash attention with block sparse attention is the first sequence-to-sequence model to achieve non-random performance on 64K context. Now let me talk about flash attention version 2. So there's a few improvements over the existing one. So if you recall from before, instead of dividing, remember how we basically loaded this and then loaded this and then loaded this, computed it, and then we computed this, but back here we divided by some L, and then here we multiplied that L back and divided by L prime, which is the sum of everything. Basically, it's saying that we don't need to do that. We just don't divide by L in the first place and wait till the end to divide by this big L. So yeah, so that's the idea here. So that reduces some non-matrix multiplication flops, which are usually slower to compute. And also another thing is that when we're doing causal masking language modeling, if we're gonna mask, this is the Q, this is the QKT matrix, and if we're gonna mask this part anyways, we never had to compute it in the first place, and we can just skip it during our for loop. And another thing that flash attention v2 does for us is parallelism. So in v2, rather than, recall that this was in the KMV, we're in the inner loop in flash attention. In v2, we keep it on the outer loop. We keep it on the outer loop because let's look at this diagram here. Consider this, basically this square, to be QKT. And if we parallelize across Q, what does that mean? That means we have one worker starting here and then going this way. Recall that before it was like, it was like going this way and this way, where we computed okay, it's fine. Where we computed like this first, and then this, 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 etc. Now what we do is we parallelize this way. So when worker 1 is done this, it can immediately go to the backward pass on this. And by the time it gets to the second backward pass, worker 2 is also done this. So then these 5 workers here, you can see, all end up doing 6 tasks, and they're all able to do it. It's possible to do it in a sequential manner because the way we arrange it. And so that's the way we parallelize it. Another feature that flash attention v2 offers is warp partitioning. So within each thread block, there are different threads. And what we want to do is we want to split across these threads across Q rather than across K. And the reason we want to do that is because when we split across Q, if each thread splits across Q, then completing this means that the threads don't have to communicate within each other. But if we split across K, if we compute this and compute this, then we still have to add them together. Whereas this, because everything's already added together for you and it's like row wise, we don't have to do the additional communication cost. And in terms of results, on the left hand side we have the forward speed, and on the right hand side we have the backward speed. And as you can see, purple is a flash attention 2, and it's much faster than any other existing method. So yeah, here's the references, and thank you.